Yeah. It wasn't recorded. I wasn't recording the first half hour. I think isn't it enough audit Manopto. They don't record automatically.
Don't if you record the Zoom.
So we lost the first half hour. So, okay, so all the jokes, they were great jokes. Okay, so we lost the first half hour, but let's live with that. So that's an exercise that the reporting groups are unimodular, and the hint is to use the classification of reporting groups via this smallest class that contain the trivial group and slow down taking center. So G modular center. So that's so let's see some non-example. So example of non-unimodular group, and actually it's also good. I use a lot today, but it's a good exercise. The group of affine transformation of the real line. So what is affine transformation of R is just translation and homotopy, and get from that. And this is the group if you want you can write it as R star semi-direct R by translation and R star. So you can also write it as the group of 2 by 2 matrices of this form, where it acts on R in this way. You can think of X as a point in R. This is R. And we see that this matrix take A, B, 1, take 1, X, so X1, AX plus B, 1. So some people just call this group the AX plus B group. Okay, so this is the affine group of the line. It's a solvable group, so in a sense it's not very complicated, but it's not really modular. That's an exercise. The way to solve it is just by writing explicitly a left arm measure and a right arm measure, and you see that it's not the same. And it's not very hard. You know the arm measure. You use the arm measure on this, which is the back measure, the X. And here, you also know the arm measure. If you take logarithm, you get the identity group, and so you know the arm measure here, the arm measure here, but also you have to combine the action here. So yeah, you will see it. I mean, it's a good exercise. So this is a group which is not unimodular, so not all groups are unimodular. Okay, so let me, before going to the main object, which are lattices.
So I think in this example like this, it's reasonable to assume that the Howard measure is absolutely continuous with respect to the Lebesgue measure when the linear group.
Yeah, it's always the case. It's always the case. The Howard measure, I mean, for Lie groups, yes, it's absolutely continuous. Yeah, you have. Okay, but here you can write explicitly like something A times B. Oh, yeah, it's almost say. I mean, depends if it's on the left or the right. Okay, so the modular character character is defined as follow. So let G be a locally compact group. And fix the power measure. Let the mu be left power measure. And then observe that by the way, I want to give another what? Never too late. So another exercise. No, okay. Let's first write it. So then you can define it's denoted by delta of G. Okay. So given G, an element, consider the measure nu, which is defined as follows: nu of A for every Borel set will be just mu of A times G. Multiply A from the right. Then, so nu is again a power measure. This is also left bound. So by the theorem of Hall, it must be the same as mu up to scale, independently of A. G is fixed, and A is any measure. A measure. So this is also so this implies by our theorem that nu is equal to some scalar which I denote by delta of G times mu. Because mu of A is for every. So this scalar is called, so this delta is called the modular character. So delta is some element in R, actually in R star or in the positive scalar. So sometimes we like to, it's nice and right that mu of A to the power of G, mu of G inverse AG is delta G times mu A, because I think from the left of the so, and then you see that delta is a character. Delta from G to R is a character, so it's a homomorphism. And G is unimodular. If and only if delta is the identical, it's trivial. By this I mean that delta of G is always trivial. Then it's only
This is a monophysium with cell group.
No, as a group, you delta of GH, it's an exercise, it's a very straightforward exercise, delta of G and delta of G.
But it's the positive section. So maybe some multiplicative.
Yeah, this is a multiplicative group. The positive real is a multiplicative group.
Okay.
This is the character, and this is called the modular character. To verify this, so this I won't even write it in exercise because just write one line and see that verify. So that's the modular character. Now, once you have this modular character in hand, and you know that this defines unimodularity, then immediately you see what I told you, like exercise before, like that the compact group is unimodular. Why? Because okay, you need to show that this character is also continuous. But this is because the R measure is very regular, then you can see that this character is continuous. And since you don't have continuous homomorphism from compact group into the real line or the into R star, you don't have non-trivial character. Except the trivial. Yeah, you don't have compact sub R except the trivial group. So we don't have non-trivial character compact groups. So then immediately you get a compact group that we move. And similarly, immediately you get the perfect group. So we don't have character for perfect group. And so on. So the exercise that were used before and maybe seem mysterious now are trivial. Some of them. The exercise about the important group is still in group. So this is the modular character. Let me give one more.
What you said about receptor, right?
Sorry?
What you said about dividing out the receptor.
Yeah. It's not a very hard exercise, but you need to say something. Another exercise.
So did you want us to do the previous exercises without the use of the modular character?
You can use them. You can use anything that I say today to show today. Yeah. I basically it was more coherent to give this exercise after, but yeah, you can use it. So here's another exercise. Is that G is unimodular. If and only if mu of A equals to mu of if and only if mu is symmetric. In that sense, that mu of A equals mu of A inverse for every measurement A. Well, A inverse by definition is a set called inverses. So that's
I have a question about the.
just a minute, and let me give you a small hint. You see immediately that this measure, if you define mu of A to be mu of A inverse, you can do it for every group, when we look at compact group. Then this measure nu is right in that. So, but if G is unimodular, if this is satisfied, then immediately you see that G is unimodular. But if G is unimodular, then this right measure is also left measure, so it's up to scale to original one, but you need to show that this scale is one. Okay. After this thing, it should be an easy exercise. Okay, what is the question?
Yes, this homomorphism is always continuous.
Yeah, I mean, when I say that the R measure is Borel regular, and once you have a measure which is Borel regular, this implies that it's regular. Yeah, it implies. You see this when you want to compute it, say, so you can take A as you like. It doesn't depend on A. Take A, a nice like compact set, and then you see that if you move it a bit, its measure change by the so, okay, so this is about very general stuff about our measure. And now, so okay, the recording didn't record the introduction, but this course is about lattices, or more generally lattices and random groups. And I repeat things that I said in the beginning, because for those students who want to watch the recording, but understand it, this course will be divided to 3 parts. The first third will be about material lattices. That some of you are familiar with part of it, but I promise to do things that you don't know, that I think you don't know. I promise to do. Like, for instance, modulus of correlation and extremely elegant proof of extremely elegant result. Says, for those of you who know that arithmetic functions are lattices. The second third will be about invariant random subgroup, which is a generalization of lattices that became very popular in modern mathematics in the last 10 years and in a very active area. Today, theory is developing, and we will think of invariant random subgroup as a generalization of lattices, and we'll do more studying the application to lattices. And the third part of the course will be non-invariant subgroup, like random subgroup with the measure. So we start with lattices. So here is the important definition. So let G is always locally comparable. By the way, we will assume also that it's second countable. That the topology is second countable. Assume that G is what's called LCSC, which means that the locally compact taken on. How does this help? In particular, G is metrizable. So to be metrizable, it's enough to be first countable. It's enough that we have a base of neighborhoods, a countable base of identity neighborhoods. You don't have to be second countable, but second countable is even more convenient. Means that it's metrizable and separable. You have dense countable set. By the way, so here is a good exercise. Right. Locally compact second countable group. It needs a left invariant measure. Left invariant. This is elementary, but not trivial. You have to use the identity neighborhood to construct this metric. It's much more elementary than how.
You mean assume that it means element? Oh
no, a group.
No, I mean, but
no,
assuming the theorem that it means element, or
no.
just pulling it means
no, yeah, prove that it admits a metric which is left invariant. I don't know. But it's maybe it's the first one.
So it's quick easy.
Okay, maybe so. They say it's not so elementary.
I don't know. No, the theorem the first one, but it's not very
Yeah.
elementary.
Okay.
Then I suppose it's very tough. So.
Okay. Yeah, this is. I don't tell you which. When I write exercise, some of them are harder and some of them are easier, but there's certainly a solvable exercise, even if it's a theorem. So it admits a left metric. Usually, a metric you cannot expect it to be also right. It's very rare that the left metric. Okay, that's this is one remark. Okay, so definition. A closed subgroup H G is called, by the way, I use this notation to denote subgroup, and this notation to denote subsets. So a closed subgroup is called cofinite if the homogeneous space given A. So this is a space that G acts from the left on this space. So this is a topological space. There is a canonical topology, which is the quotient topology. So a set here is open if and only if it's framed in G. Right? And G acts on this space. And so H is called cofinite if this admits and G invariant finite. Usually we take it when it's finite. You can when it's finite you can scale it to be 1. So the G invariant probability. So then it's called cofinite. Now, an important definition for this course, a lattice is a discrete cofinite discrete cofinite subgroup. In discrete, then of course it's the closed, and the discrete group is subgroup closed. And so that's the definition of it. So it means that usually we denote lattice by gamma, and the space G mod gamma is the G space, and it admits G invariant probability value. Then gamma.
G left and down.
Yeah. I mean, G acts only from the left. In this space, G acts from the left. Okay, another definition, H closed subgroup H G is said to be uniform if for compact, i.e. G mod H compact or equivalently there is C in G compact such that C and H. Then we say it's sometimes we say uniform and sometimes we say property. And let's see some examples.
You can refer to it written with uniform plus subgroup is lattice.
Okay, let's discuss this. So before that, this exercise will allow you to solve this exercise. discrete group, discrete subgroup, gamma and G always admits fundamental domain. What is a fundamental domain? i.e., a measurable set omega, which consists of coset representative of gamma. So, such that the disjoint union of omega, gamma, gamma, and gamma equals to G. Like if you want, so that's an exercise. It's helpful to use the metric, it's not necessary. Construct such a set. And for example, you see for the action on Z2, on R2, this square is the fundamental domain because the tessellation of the translate of it tessellate the ball. But if you want to that it will be really disjoint, then you will take some of the side of it and not all of them. And then you get the precise fundamental domain. And since we care up to things up to measure 0, sometimes we allow, when we write this to be disjoint, we allow intersection, but only of measure 0, and then we can take it close.
You need H to be normal in G or?
No, it's a closed subgroup.
Okay. So when you say G mod H, you mean
The G mod H is not a group. It's a topological space where the quotient topology and the circle will open if it's going the G.
Okay. And can you always take, like the case in Z2 and R2, can you take omega to be some connected set, or there are?
Sometimes, no. Sometimes, of course, sometimes we will consider, soon I will give a list of examples, but we also will consider groups which are totally disconnected. But you ask, yeah, if you want, if G is connected, you can always take the fundamental. And okay, so let me now give another so exercise. Gamma G, a discrete subgroup gamma. Before that, I need to tell you more facts. Like how measure, the measure on G mod H, G mod H in general, if you take a subgroup H and you consider the homogeneous space G mod H, it doesn't have to admit G invariant. Usually it will not admit. But if it admits, this measure is unique up to scale, just like in Harvard. And all this stuff are very well presented in the first chapter of Weizmann. So I will not put it here, but let me at least state a lemma in Weizmann that say the following. G mod H meets a G invariant measure, or actually, let's even say it more generally. A measure, or let I from G to R be held. So that's a whole fill them to the multiplicative group. measure u on G space X, let's say X is a topological space in which G acts, and it has let's say the wave structure, and the measure on its call is chi quasi-invariant or quasi-invariant with character chi if for every A in X measurable and every G in G, we have that mu of GA is chi of G. Such a measure is chi quasi-invariant, and we say that the measure is quasi-invariant if there exists such a chi. Yeah. In particular, yeah, a measure is quasi-invariant if mu of GA divided by mu of A is independent of A. Then you say that the measure is quasi-invariant. And then this will define how. So that's the definition of quasi-invariant. And then the lemma and the measure is invariant, if it's quasi-invariant with respect to the trivial term, right? That's invariant. And the lemma that you can find in Raghunathan's book, I could do it here, but it will take a full hour and a half, actually more than half. We take 2 hours to do it here with details. So I send you to Raghunathan's book to read the following important lemma. And so I refer to Raghunathan's chapter. One. But there are many other nice stuff about lattices. So about confined lattices. So let G be a locally compact group, and H no subgroup. Then G mod H, it means wait, so actually, okay, let chi G be a character. G mod H admits a chi quasi-invariant of a measure, I mean non-trivial measure. If and only if positive and open and finite and compact, like how we have. If and only if chi of H equals delta G of H divided by delta H of H for every H in H. That's the condition. So this is the modular character of G. This is the modular character of H. And the portion of them is the character of an H. So you have this is a character on H. So in particular, if you have a quasi-invariant measure on G in homogeneous space, G mod H, it means that the corresponding character to be fitted to H must be this. And if you take a general situation where G is a locally compact group and H is equal subgroup, you look at that and you have this character on H and you ask yourself whether this character extends to G. If it extends to G, then you can then there is such a measure. If it extends the character to G, then you can find a R measure for G. So this is a very useful lemma. The proof is technical, so I skip it here. I'll send you to the book. And in particular, G mod H admits G mod H, the homogeneous space admits an invariant measure, G invariant measure, if and only if the modular character of G, if you restrict it to H, equals the modular character. So sometimes you have groups that this character do not extend, so the homogeneous space will. But sometimes you see immediately that the character extends. For instance, if H is unimodular, then the character of H is trivial. Then you can take this chi to be the character of G. So if H is unimodular, then the homogeneous space always admits quasi-invariant. Particularly if H is discrete, then you always have quasi-invariant. So G mod gamma always admits a quasi-invariant measure and actually an invariant measure. So if H is, it's actually admits an invariant.
Why?
What?
Why?
Why G mod gamma admits an invariant measure? Because you can,
If
if it's discrete.
I can't talk about
No, if gamma is discrete, you can actually use the Howell measure. That's the next exercise for you. Follow the exercise or not? So here's an exercise. When gamma is discrete, you can use the Howell measure on a fundamental domain to define the measure of the quadrant. So in particular, let me the following. So discrete subgroup gamma in G is a lattice. If and only if it admits a finite volume, but volume I mean Howell measure, fundamental. You have gamma and you have omega, which is fundamental domain, so the union of that equal G, and then you can use this omega if you want omega to reject onto G mod gamma bijectively, and you can use you can take a set here and put it back here, and you see its measure, and that's how, and you do the measure here, and that's how you get the measure in G mod gamma. It's fine. So that's how you define the measure in G mod gamma, and it will be left invariant, and so that's an exercise for you. To show that this is equivalent. In particular, I want to give some examples of lattices before the end of the talk, but let's give a couple of more lemmas. So, before the lemma. Okay, lemma. Any two fundamental domains, if gamma is a lattice, then the core volume is well defined. What do I mean? And omega 1 and omega 2 are fundamental domains, two different fundamental domains, then they have the same. Then the R measure is the same. And the proof, let's say proof. So mu of omega 1 is, so if you want omega 1 equals this joint union of omega 1 affected with omega 2 translated by gamma 1 over all gamma. Okay, maybe I don't give this the right way. So okay, and then omega 2 I can write as the union of gamma inverse or omega 1 gamma inverse is actually omega 2 gamma, which you see if I take this set and just translate it. So you see that the same. So that's it. I take the first fundamental domain, I write it as a countable union or a finite union of these sets, and then move them. Okay, so this implies corollary.
How do you need with the countable union?
Gamma is countable. Gamma, I assume that G is second countable, so every discrete group must be countable. Yeah. So here, this is a presentation of omega 1, and this is a presentation of omega 2. But you see, what is this set? This set is exactly gamma. Is exactly that set.
It's omega 1 gamma inverse.
Yes, yeah, you're right. I need to tell you something before. I need to tell you that I assume, let's suppose, okay, for the proof, the proof was assuming mu is a right hand measure. Right? If I took a right hand measure and
Assuming G is unimodular.
so I don't want to assume it because I want to okay. So this
You mean gamma is a lattice for some left-right measure?
wait, that's okay. Assuming mu is a right hand measure. By the next lemma, we base it.
Where mu is assumed to be a left-hand measure, and you assume
No,
mu here is a left-hand measure in the statement,
yeah.
and then
mu is a left hand measure, assuming, let's say, G is union.
Why couldn't you multiply from the right gamma instead of multiply gamma from the left?
you didn't multiply. You just want to use the measure is the same.
Yeah.
Domain. No, we define fundamental domain from the
Let's leave it like that.
from the right.
Let's leave it like that. You will only have a problem with it for 1 minute. Believe me, because the next lemma, okay, maybe I should say, no, I'm not cheating, but I'm not.
I think the proof is going to be
No,
the fact that
okay, let me complain at the end. Okay, if you still complain at the end. But let's see the next lemma. That if gamma, if a group that admits a lattice, is fully modular. And why? So you proof. Let U be a right R measure, like we use here for that proof, and let omega be, or before that, yeah, let omega be a fundamental domain. Then also G omega is a fundamental domain. So they have the same measure. So mu of G omega equals mu omega. So I took the right R measure and I show you that it's like that. So if a group admits a lattice,
So you use the previous one, no?
yes, it's exactly what you just proved.
Yes, it's the previous one.
what?
This is what you proved now. So we give you model.
No, here I assume that that mu is a left variable. For this, I just need, if I take
So why G omega is a fundamental domain?
no, G omega is a fundamental domain, that's obvious. Because G omega is fundamental domain just by fundamental, it's a fundamental domain for the action on the right. For this, no, I didn't use,
No,
I didn't use, maybe somewhere else I cheated.
No,
But
the previous lemma said the measures are equal.
what?
The previous lemma told you that if they are both fundamental domains, then the measures are equal.
Yeah.
No, but in the next lemma you need only the new right invariant. If you have you always have a right invariant R measure, you use it.
I think if I'm cheating, then the next thing will solve this.
למה צריך
שוויון של
בסדר, אבל
Another lemma, very easy lemma, that maybe you need to put it here to fix some cheating. I don't know, maybe you don't need. But lemma, if G not H admits a finite quasi-invariant
אני לא רואה סיבה שזה. לא יכול להניח שזה
measure, then the measure is invariant. So that's maybe I'm also using this lemma. If you have a finite quasi-invariant measure, then it must be invariant because the character must be trivial. Suppose you have a finite quasi-invariant, then with respect to some character chi, you can look at the space itself. You see, it has some measure, but then you multiply it by G. Then on one hand you get chi of G, mu of G mod H, but you see it's the same thing. So chi equal to 1. So maybe I'm a bit. You need to check the detail, but if I cheated, then this will solve it.
Then you won't catch.
Because okay, then this will allow you to move from left to right because in the previous. Okay, so let's suppose we agree with that. We have another 10 minutes before I we go to see there's no place left in top. And so maybe I want to give some example of lattices for the end of, but maybe another exercise. It will be again easy exercise now. A uniform speed subgroup. Subgroup is a lattice. And it's immediate because you have a compact fundamental domain. So it's a why do I want to give this exercise? Because it's not true that every uniform subgroup is cofinite. So for example, take G to be SL to R and H to be usually we call the Borel subgroup, which is the group of upper triangular matrices. That's the Borel subgroup. And then H is uniform. U and H is what we call the projective line, but not confined. So the projective line is a G space that does not admit an invariant measure. The action is actually very contracting there. Yeah, there is no left invariant measure on the projective line under the action of SM2R. So it's an example of a uniform subgroup which is not confined. So, as opposed to this exercise where the uniform subgroup is discrete, then it is confined. Okay, let's give some examples of lattices before I send you home or to the top. Or do you want me to finish now? So we okay. So my assumption that it will be very crowded, but okay. So if G is yeah, if G is a compact, G is compact, then every closed subgroup is cofinite. What are the lattices in compact group? Define some. The lattices are the finite sum.
This is the proof G is another proof G is minimal.
Yeah. Okay, if G is abelian, then H in G is cofinite if and only if H is uniform. Why? Because G mod H is a group. So a measure on G mod H would be a Haar measure on G mod H. And we had an exercise that the Haar measure on G mod H is finite if and only if G mod H. The Haar measure on the group is finite if and only if the group is compact. So since the proof is that G mod H is a group. So
only uses that H is normal. Right?
Yes.
So any normal confinite is
exactly. Yeah, if you want to. Yeah. Okay. That's it. Remark, 2 prime, and normal. Sub is so finite if and only if it is a slightly more interesting example. Let G be the Heisenberg group. So it's a unipotent three-dimensional group. A, B, C. So A, B, and C are in R. That's a important group. And this is called the Heisenberg group. And gamma will be the same thing, alpha, beta, gamma, well, alpha, beta, gamma with Z. So this is a uniform lattice. And to see that it's a lattice, you just need to find a compact fundamental domain, and it's very easy here. You just take, you allow A to be between 0 and 1, B and C, and then you get a compact Q, that's the fundamental domain for this lattice. That's another example. I want to give you also I want to give you some more interesting example, but I do want to finish what it do. So let me just finish with one more classical example. So far we only have example of uniform lattices. So for SL2Z inside SL2R is a non-uniform lattice. So it's a lattice. Actually, with respect to a natural R measure here, the volume of it is pi over 3 actually. And it's a lattice. The quotient of the hyperbolic double half space is called the modular surface. It's a very classical example. We will prove that it's a lattice, but it's not co-compact. It's an example of a non-co-compact lattice. It's the first example. So just you leave this lecture knowing that such feature exists. So but I will prove that it exists. Actually, this is an example of an arithmetic group, and we will prove that every arithmetic group exists. Yeah, so I wanted to give more examples, but I'll do it in the beginning. Okay. Yeah.
טיפה תכבו את ההקלטה שם.
fundamental domain is the
אני לא שייכת שום דבר.
כן,
כל כזה.